Okay, now resuming from where I left, the weight for correct classifications, the new weight will always be less than the old weight, and the for incorrect classification, the new weight will always be greater than old weight. So, in order to avoid the calculations, I'm just going to come up with something. For remember, we had four observations. The weight was 1 over 4, 1 over 4, 1 over 4, 1 over 4. And after applying that formula for one incorrect, let's say, classification and rest of the right classifications, correct? So we know that the new weight of incorrect classification would increase. So half, it was 0.5. Let's say it become 0.33. And it was half for the correct classification. So it would decrease. So let's say it decreased from 0.25 to zero point 0.2. This sum, now this new sum, after applying this weighted formula, e to the power minus significance, weight into e to the power minus significance, would not sum up to 1, right? So our first thing what we have to do is to normalize this to so that all of this should sum up to 1. Now 0.3 plus 0.2 plus zero point 0.2 plus, so the good thing about normalizing is we simply sum it up, 0.2, 0.6, 0.93, and divide each observation by 0.93. When we divide each observation by 0.93, divide by 0.93, divide by 0.93, the final answer which we'll get after normalization of the new weight would actually sum up to 1. For example, the new answer is 0.31, right? And it is 0.18, 0.31, not 0.18. Let's say I keep it 0.19, 0.19, 0.19, 19, 57, 80. No, so I'll keep it 0.32, 3, 20, 50, 70, 90. Let's say I make it 0.38. I am not doing the actual calculation, but if you do the actual calculation and divide each value with the sum of all value, the final resulting should actually sum up to 1. So these are the new weights. Now you see these are the new weights, and the weight of the incorrect prediction has significantly increased. Now we'll do the full process again. We'll again check. We remember we had, so these are the new weights, and we had A, B, C, A, B, C, gender, and age. We'll again calculate the Gini index, which is fine to get Gini index to see which one to. Plus, now how we will use this increased weight in the next predictor. That is the trick. So to use this increased weight in the next predictor so that this particular observation gets more priority is for next one, we again take what is the basic of an ensemble. We take equal number of observations for the next prediction. So when we take equal number of observations, we know that for 0.19, I mean, just see how it works. So there is a 0.38 chances. I'll keep it simple. So 0.38. I'll simply add these up to make it a cumulative probability distribution. 0.38 plus 0.19, it is 0.48, 0.57, then it is 0.76, then let's say this is 1. Okay, when you add this up, I mean these two, then these three, then so this is the cumulative probability distribution which comes up: 0.38, 0.57, 0.76, and 1. Now for the next four predictions, I mean to check from where you have to take the values, we just take four random numbers between 0 and 1. Let's say I take zero point 0.5. If I take zero point 0.5, it is falling between these two, 0.38, 0.5. So I'll take second observation as my first observation. 2, 3, 4. So I'll take second observation here. Since 0 to 0.38 are covered within first observation, there is high probability that I'll take the first observation again and again. For example, next value which I think of is 0.12. I'll take first observation. The next value which I think of, the random number, is 0.25. I again take first observation. And the next value which I take is 0.9. So I'll take fourth observation. So this is a new data set in which one observation is repeated. Now you see how weight has impacted. Since the weight has increased for this incorrect classification, in the next classification, we have more more observation from the incorrectly classified ones. Now since we have more observation from the incorrectly classified ones, now we again calculate the Gini index based on these. Now the new decision stump will actually be able to give more weightage to, more tilted to this one, and will actually correctly classify these two, but might incorrectly classify this one. So again we go through the full process. Again we do the weights, and that's how the whole cycle goes on until it a comfortable number. When it comes to Python, let's say we give it 200. So 200 times it has to do this full cycle. After doing 200 times this full cycle, this is how our final model should look like. The final predictor will look like something like this. The weight which we got the first time, the alpha one, right, multiplied by the decision stump, we had the output of the decision stump. For example, it was saying yes, and the weight which we got, the significance, which is nothing but log odd function, it was, right, it was log odd function. So the value of log odd function is an let's say if it is from it ranges from 4 to -4, right, -4 and 0 in between, and the values of the odds go from 0.01 to 0.5 to 0.99. That's how the values of this. So when the values of this goes, this is the effective weight which log function gives. Okay, don't cram it. I'm just giving you a high level approximate value. So alpha, let's say if it was a good predictor, so it gave more weightage. So so the first one, the decision stump, the weightage was alpha 1 was, let's say, 2. So twice of, we'll take the result of twice of first decision stump plus again new alpha which we created. Let's say it was 1.6 into decision stump 2, right? Then next one, which is, let's say it was a bad predictor, but it kind of, why? So now you'll see the value of this predictor will actually depend on earlier one. So why this can be a bad predictor and this was a good predictor? Because it was able to correctly classify the incorrect classifications of this one, but were heavily failed on the ones which were correctly classified by this predictor. So this is, let's say, -2 into DS3, and likewise 200 times. Now this is totally and totally my observation. I mean, this will give you the final result, giving weightage to each decision stump and giving you a final answer of this thing. Now, this is totally my observation. Now, check this out. If you see, this is a linear equation, correct? If I break this down, if I simply, for example, I am doing a linear regression with 5 variables, let's say 3 variables just for the sake of it, our polynomial linear regression equation would look like something like this: 2x plus 3y minus 2 5z is equal to y, something like this, right? Not y, outcome. I can break this equation to say 1.5x minus plus y minus 3z plus 0.5x plus 2y minus 2z equals output. Just check this out. Doesn't that look like a adaboost classification, although this was a linear regression? We give 1.5 weightage to one variable. Now, based on that, we give we create another we move on to next step, and we found there is totally no weightage needed for next variable. Then we come on to the third variable after this. Likewise, chain is going on. So if this also, when you are going to solve this, it actually comes down to alpha 1 plus alpha, let's say alpha 3 something something, into decision tree 1, which was nothing but first feature, first decision stump, plus alpha 2 plus alpha 4 plus something something decision 2, and likewise is going to give you the final output probability. So that's how you can relate this to linear regression, although two totally different things. But see, what they have done in adaboost is basically, when you give weightage to each feature, correct, may it be a classification feature, may it be a regression feature, x and y in this case, that's how the model comes. So adaboost is nothing but a linearly regressed classified decision stump. I'll repeat: linearly regressed classified decision stump. That's how you get the final output. And it is very, I mean, someone applied a lot of brains, and what he ended up doing is he simply reapplied the basics on classification. He basically reverse engineered the linear regression and came up with something like this. So I won't expect anyone to get what all I said in both of these videos in one go. So I'll suggest to go through those videos couple of times. And there are many other videos on YouTube and in book also. Books also it's given, but in YouTube it is more, you'll get a more intuitive sense of the math, what is going on. So that'll help you. Now the last thing, remember I left it for the last, learning rate. Learning rate, eta log odds. I'll call it log odds, simple. Now think, what will this do? If I simply, this value is between 0 and 1, fine. So if, and I know I am going to calculate this log odd again and again. So the smaller I keep this value, the smaller steps it is going to take. The bigger I keep this value, it is going to take bigger steps. For example, if I keep it 0.7, let's say, like 1 in place of 0.5, I keep it 0.7. The graph. So this is what we have to actually attain. right? This is what we actually have to attain, that something here is what we are going to get our final optimized model. If we keep the learning rate small for a boost algorithm and we use all other features, this is the jump you are going to see. Returning back to optimum point. Smaller step. If I keep the learning rate bigger, this is how it's going to happen. So that's the whole point of learning rate. Bigger step, you take learning rate value as bigger step if you have a very good, very pure decision tree coming up. You know it is very good. I need not check each and every observation, so I'll simply jump. So ideal case scenario, the bigger step, if you take it the right model, this is how it is going to help. So in two iterations, you reach the final point. This is the ideal case scenario if you take a bigger step. But generally, you take a smaller step so that you make sure you don't miss optimum by a long shot. Okay, so that should be it, guys, and that's why learning rate log of odds. This is taken as zero point 0.5 generally, 1.5, sorry, 0.5, just so that the steps are small. Okay. Okay. Let me know if you have any questions. Gradient boosting, I'll try to come up later if you have doubts, or else I'll not.